Today we want to talk about what happens when charged particles move through an already existing magnetic field. We call that an external magnetic field. In fact, that magnetic field that's already existing, that external magnetic field, we're going to call B1, magnetic field number 1. The moving charge, however, also generates a magnetic field. We're going to call that magnetic field B2. So B1 is already there. B2 is produced by the moving charged particle. If the charged particle is moving through B1, the already existing magnetic field, then we're going to have two magnetic fields interacting with each other. B1, that was already there, interacts with B2, the magnetic field that's been generated by the moving charge. That will produce a force. And what we're going to see today is a method for determining the magnitude and the direction of that force. Let me draw an example of this. Let's say that we have a magnetic field produced by these two bar magnets. In between these two bar magnets, the magnetic field would point to the left, away from the north and toward the south. Remember, that's B1. That's the external magnetic field, the one that was already there. The source of that external magnetic field could be, as in this case, two magnets. It could be the Earth. It could be whatever. Another electromagnet, whatever. It's a magnetic field, however, that's already there, an external magnetic field. We do have, in this question, a charged particle. Let's make it a negatively charged particle going into the page. That will generate another magnetic field. It's going to be circular. And if we use the wire grasp rule, not the deflection rule, this new rule that we're going to learn about, but the wire grasp rule, we would say that that green magnetic field, the magnetic field generated by the moving charge, is thumb, fingers, counterclockwise. So now you get these two magnetic fields, the one that was already there, B1, and now the new one, B2, that's generated by this moving charge. They will interact to produce a force. Which way is that force? Well, intuitively, we might like to say that the force is either with the field or against the field. That would be the case if it was an electric field, but it's not an electric field, it's a magnetic field. So the magnetic force is not with or against the field. We might like to say that the magnetic force is in the direction the particle is moving or opposite to the way that it's moving, but it's not. It's a little bit counterintuitive, but in this case, the magnetic force is actually going to be downwards. But why? Why is it downward? We got a field that's to the right. We have a particle moving into the page. We have a force downward. We need a way to predict that. It's not as simple as saying, I'm positive the force is with the field, or negative particle experiences a force against the field, as in the case with the electric fields. Here's where we're going to use the hand rule for deflection. And here's how it works. The next slide will give you a summary of it. So don't worry about writing it down right now. Just kind of work along with me to make sure that you can actually do it before we write it down. Thumb goes in the direction of the moving charge, which in this case is into the page. If it's a negative particle, you would use your left hand. If it's a positive particle, you would use your right hand. Thumb goes in the direction of the moving charge. Your fingers, which are not bent this time, this is our third rule, and for the first time we're using our fingers straightened out, not bent. Our straightened out fingers will go in the direction of the magnetic field, the external magnetic field, B1. Thumb into the page, fingers go to the left in the direction of the external magnetic field. My palm, that's the third variable here, the first time we're using that one. My palm will automatically point downward. So we would say in this case, the magnetic force is downward toward the bottom of the page. Does that make sense? Okay, let's summarize that. Let's write it down and summarize it. And then we will take a look at a couple more examples, a number of other examples actually, to make sure that you've got this down pat. So we say we use the hand rule for deflection to find the direction of the magnetic force on a charged particle moving perpendicularly through an external magnetic field. I'm going to highlight this, and I'll come back to why it's highlighted in just a moment. What are my variables? Well, my thumb. My thumb points in the direction of the moving charge. My straight fingers, not my bent fingers, for the first time my straight fingers will point in the direction of the external magnetic field. That was magnetic field number 1 that was in the example that we just showed you on the previous page. Remember, there's 2 magnetic fields here. There's the magnetic field that was already there and the magnetic field generated by the moving charge. My fingers point in the black magnetic field here, the magnetic field that was already there, the external magnetic field. And my palm will always point automatically. I don't have to worry about where to point my palm because it will automatically point in the direction of the magnetic force on the particle. Let's go back to this. Why does it say the hand rule for deflection is used to find the direction of the force on a charged particle moving perpendicularly through an external magnetic field? Here's the thing. This hand rule for deflection is valid only if it's perpendicular. If parallel, in other words, if the charged particle is moving this way and the magnetic field is also pointing this way, or the charged particle is moving this way and the magnetic field is opposite to that, if they're parallel, the hand rule doesn't work. But the good news is, if they're parallel, the force is 0. So you don't need a hand rule to determine a direction of a force that doesn't exist. If they're parallel, that's what you should hope for. If they're parallel, there is no force. No magnitude of the force, no direction of the force, there is no force. If they're perpendicular, there is a force, and you have to find its direction by using the hand rule for deflection. If they're not parallel or perpendicular, in other words, if the charged particle is moving this way, and the magnetic field is 37 degrees from it, there is a way, but we're not going to learn about it in Physics 30. So there's an infinite number of possibilities, but for you in Physics 30, only 2, perpendicular or parallel. If they're perpendicular, use the hand rule for deflection. If they're parallel, the force is, there is no force. The force is 0. Got it? Let's do a few examples here, all right? Let's say the first one, we've got a magnetic field represented by these arrows pointing toward the bottom of the page. We've got a negatively charged particle moving to the right through that magnetic field. Is that particle moving perpendicular to the field? Yes, it is. So we can use the hand rule for deflection. If it was parallel, we wouldn't need to use the hand rule because the force would be 0. If it was neither perpendicular nor parallel, it wouldn't be a Physics 30 question. This is perpendicular. We can use the hand rule for deflection, and here's how we do it. My thumb points in the direction of the moving charge. Point my thumb to the right. My fingers will point in the direction of the external field, which is toward the bottom of the page. Which way does my palm point? Out of the page. Now for me, for my page, which is vertical, it's pointing this way, right? For you, whose page is horizontal, it's pointing this way, right? Thumb fingers this way. But any way you look at it, for you or for me, it's still out of the page. That make sense? My frame of reference is the page. So therefore, my answer has to be expressed relative to the page. Don't say it's up. Okay, it's out of the page. And that way, it doesn't matter which way your page is set, either horizontal or vertical, like mine is. Okay, let's try another one. Let's say this time we have a magnetic field represented by these X's. Let's say we've got a charged particle, once again, moving to the right, but we'll make it a positively charged particle this time. Is that charged particle moving perpendicularly through the magnetic field? Yep. A charged particle is moving this way, magnetic field is this way, that's 90 degrees, that's perpendicular. So we're allowed to use the hand rule for deflection. Which hand do we use? My right hand, because positive particle. We're going to stick our thumb towards the right in the direction of the particle. My fingers are going to point which way? In the direction of the field, which is into the page. Thumb to the right, fingers into the page, palm points which way? Yes, good answer. It's not up. It's not pointing up because our frame of reference is the page. My palm is pointing toward the top of the page. Or you could say up the page, toward the top of the page, up the page, but don't say up. Because our frame of reference is the page. If our frame of reference was the Earth, we had a question involving north, south, east, west, then we could say up or down. But if it's the page, we have to express it relative to the page, toward the top of the page, out of the page, to the right side of the page, to the left side of the page. Let's try another one. We have a magnetic field pointing this way. We have a positive particle, once again, positive particle going this way. Magnetic field going down the page, particle moving up the page. What's the direction of the force here? There is no force. Good answer. There is no force. Why is there no force? Because the particle is moving parallel to the field. There's no hand rule to do when it's moving parallel. Yep. Ask me that question in another 20 minutes, a half an hour when I show you the equation. Okay, then I can mathematically justify that to you. Okay. All right, let's do one where we have a north, south, east, west frame of reference, not the page, up the page, down the page. Okay. Let's say that we have a charged particle, a negatively charged particle traveling to the north. By the way, when I say north, what I really mean is magnetic south, right? Okay, if I say north, I mean geographic north. Okay, that's north, right? You can look out there and see the mountains, so that's west. North, west, south behind us, and that's going to be east over there towards Saskatchewan and Manitoba, both of which, if you get on a high enough building, you can see from here. We've got a charged particle, a negatively charged particle going to the north, this way. Thumb this way. We've got a magnetic field pointing to the west, this way. So thumb, fingers this way. Palm's going to point which way? Down. We're not going to say down the page this time because our frame of reference is the Earth, north, south, east, west, right? We do the hand rule the same, but we express our answer differently. When our frame of reference is the page like this, it's toward the bottom of the page, into the page. Now my frame of reference is the Earth. You could say down toward the Earth, but because the Earth doesn't move like a piece of paper does, it's okay just to say down. Thumb, fingers, palm points down, good enough. Is that right? Don't draw this. On second hand, do draw it. Make sure you get all these little islands here perfect. All right? No, don't draw it. The reason I've put a map of Canada up is because we all know more or less what this map looks like, right? In our minds, we all know that we might get a little bit confused about exactly where Prince Edward Island is or something like that. I hope you don't. But that's not the end of the world for these purposes. We all know that Eastern Canada is over here. New Brunswick, Nova Scotia, Prince Edward Island. Western Canada is over here, Alberta and British Columbia. Northern Canada is up here, okay, although really that's magnetic south, but we call it north, right? And of course, the south is down here. The United States below us is down here. North, south, east, and west. Now, why do I put this on the board here right now? Sometimes we find ourselves trying to answer a question involving north, south, east, west of the Earth, but we don't necessarily know which way is really north. In this room, it's easy because you can look out the window and see the mountains. And that can remind us that that's west. Therefore, that's north, that's east, and that's south. But what if you go to the exam room? I don't know whether you're going to write in the cafeteria or the gym. Okay, what if you go to the exam room and you kind of get turned around and you're like, I don't, which way is north? I don't know which way is north. Make it up. Make it up. As long as your east, west, and south are consistent with it, with your definition of which way is north, it all works out. So let's say, don't look at that window. Okay, let's say you're in the exam room and you get the following question. Particle is moving to the north. There's a magnetic field to the east. Which way is the magnetic force? You get that question and you say to yourself, I don't know which way is north. How do I do this? Whatever way you're looking can be defined as north. Okay, you're looking this way. You know that's really south, right? But let's make it north. If we make that north, then we picture the map in our heads like this, then that's got to be west, that's got to be east, and that's got to be south. Got it? So we've got a charged particle going to the north, thumb to the north, fingers point to the east because the magnetic field is to the east. We know that that's really west, but in the exam room, maybe you don't know that that's really west. Okay, we're assuming east is 90 degrees to the right of north. My palm will automatically point which way? Up. That make sense? So we've made up the directions, but when we picture the map in our minds, we remember that east, however we're making up north, is going to be 90 degrees from the north. And west will be 90 degrees the other way from the north. Right? All right, you guys are going to work on worksheet number 11, questions 1 to 8 for the next few minutes here, please. Have a look at number 1. It says an electron travels to the right of the page to a magnetic field that points into the page. Which way is the magnetic force? The frame of reference is our page, so we have to express the answer in terms of the page. We have an electron, a negative particle going to the right. We have a magnetic field that points into the page. So we're going to stick our left thumb, it's a left-hand rule because it's an electron, our left thumb to the right, our fingers are in the direction of the magnetic field into the page. Our palm points which way? Down the page or toward the bottom of the page. I'm just going to say down the page, but it's not okay just to say down. For me, it's down, but for you, with your page on your desk, it's not down, it's toward the back of the room, right? So we want to say down the page, because that expresses the same answer no matter who's doing it, and no matter how their page is oriented. Let's take a look at number 2. It says an electron travels into the page. Once again, the page is our frame of reference. Electron is traveling into the page, a magnetic field that points to the left. Which way does the magnetic force point? We're going to say thumb in the direction of the particle, which is into the page. Fingers in the direction of the magnetic field, which is to the left side of the page. Palm points which way? Down the page again, or toward the bottom of the page. Let's do one more, and then I'll let you go for a few more minutes working on these yourself. An alpha particle, which we know is a right-hand rule, because it's a positive particle, travels toward the top of the page to a magnetic field that points out of the page. The alpha particle is going up towards the top of the page. The magnetic field is pointing out of the page. We're going to say right hand, thumb up towards the top of the page, fingers out of the page, palm points which way? Towards the right side of the page. Actually, let's do one more. Let's do number 4 as well. 4 says an alpha particle, once again, it's a right-hand rule. Alpha particle travels to the north through a magnetic field that points to the west, which way is the force. This time, for the first time, our frame of reference is not the page, it's the Earth. So this is where we got to think about that map of Canada. Okay, you can't see outside, you can't see the mountains out there, you don't know which way is north or east or south or west. We're going to just arbitrarily make that north. If that's north, then this would be, that's Ontario over there, right? That would be east. This is BC over there. That's west. Okay, that's The US down there, that's south. We've got an alpha particle going towards the north. We've got a magnetic field going to the west, right, towards BC, which is 90 degrees to the left of north. Palm's going to point which way? The right-hand rule, right? So it's the right hand. Okay. Palm's going to point up. Not up the page, but just up. Because remember, our frame of reference is the earth, not the page. Okay, I'm going to leave you now with 5, 6, 7, and 8. Give you a few minutes to work on those, and then we'll take a look at a couple more of those questions before we move on. So have a look at number 5. It says an electron traveling north. Again, our frame of reference is the earth this time as opposed to the page. So our answer will be relative to the earth. The electron travels north through a magnetic field that points to the north. It's the direction of the magnetic force. Trick question. What is the direction of the magnetic force? There is no magnetic force because the field is parallel to the direction of motion. Good. No force. Six, an alpha particle travels out of the page to a magnetic field that points into the page. What's the direction of the force? There is no force because, once again, they're parallel to each other. So there's no hand rule to do to find a non-existent force. 7, an electron traveling to the east. So our frame of reference is the earth, not the page. Electron traveling to the east. And we're making this north, right? If that's north, then that's east. My electron is traveling to the east and a magnetic force to the north. It's not my fingers to the north, it's my palm to the north. Thumb to the east, palm to the north, fingers point in the direction of the magnetic field, and that is which way? Up. Not up the page. Just up. Just up. Away from the earth, gentlemen. Away from the earth. We don't have to say away from the earth because up infers away from the earth. Number 8, an alpha particle. So this is a right-hand rule question. An alpha particle traveling into the page experiences a magnetic force to the right of the page. Page is our frame of reference here. There's a magnetic force to the right. So we're going to say right thumb into the page, right palm, not fingers, palm, because we've got the force direction. We're looking for the field direction. So right thumb into the page, palm to the right. My fingers will point which way? Up the page or toward the top of the page. So the magnetic force is toward the top of the page. We don't say up because our frame of reference is the page. We say up the page or toward the top of the page. Is that okay? Okay, we're going to finish off class today with just an equation that describes the magnitude of this force. We won't go anywhere with that. We'll do some problems involving the magnitude of the magnetic force tomorrow, but I just want to touch on it today so that we're kind of ready to hit the ground running tomorrow. The direction of the magnetic force acting on a charged particle moving through a magnetic field, if they're perpendicular to each other, can be found by the hand rule for deflection. If they're moving parallel to each other, then there is no magnetic force. The magnitude of the magnetic force can be found by the following equation. Fm with absolute value signs around it. Why? Well, because the equation won't give us direction. Force is a vector, but the equation doesn't tell us the direction. That's what we use the hand rule for. It's okay. Okay, the magnitude of the force is equal to Q. What does Q stand for? Yeah, the charge of the particle. And that's going to be measured in coulombs. Times V. What does V stand for? The speed of the particle. And that's going to be measured, of course, in meters per second. If you're not in meters per second, then you got to convert it to meters per second. Then we've got B, the external magnetic field strength. And that's going to be measured in T, Tesla. Now, there is an equation or a trigonometric function on the end of that as well, sine theta. But you're going to see in the questions that you do, we can drop that. Here's why. Theta stands for the angle between the way that a particle moves and the direction of the magnetic field. We've said the hand rule for deflection is valid if the particle moves perpendicular to the field. If they're perpendicular, what's the angle? 90, right. What's sine 90? Okay, so the equation, if they're perpendicular, becomes Q times V times B times 1, which is QVB. So if they're perpendicular, we can drop that sine theta because the angle is 90 degrees, which makes sine theta 1, which makes the equation equal to QVB. If they're 90 degrees, we'll tack on a little upside down t there to remind us that that form of the equation is only valid when they're perpendicular to each other, when the particle's moving perpendicular to the field. Now, again, don't write this down yet. I'll give you a chance in a second to write it down. Let's go back to the original equation. What if the charged particle is moving parallel to the field? What if the charged particle is moving this way and the field is this way? What's the angle? 0. What's sine 0? 0. What's QVB times 0? So if they're parallel to each other, by the way, if the particle is moving this way and the field is this way, what's the angle? 180. What's sine 180? 0. So if they're moving parallel, then the force is just 0. There is no equation to use because there is no force to find the direction or the magnitude of. Now, if they're not perpendicular or parallel, let's say the angle is 37 degrees, then we would have to stick with the equation QVB sine theta and stick in the 37 degrees in for theta. The good news is we don't have to deal with that. The only questions we're ever going to see in Physics 30 are problems involving a field that is parallel or perpendicular to the direction of motion of the particle. So you're either going to say no hand rule and no equation because they're parallel, or you're going to say use the deflection rule and QVB because they're perpendicular to each other. You're never going to have to stick on the sine theta on the end of it. If you look at your data sheet, this is the form of the equation that you'll see. Because your data sheet assumes that the particle is moving perpendicular to the field, and it also recognizes that if it's parallel, there is no equation to write down.